We're talking about non-deterministic polynomial time, and you've probably heard the statement NP versus co-NP, and I've had various numbers of slides on this throughout the years, and we're just going to do a quickie here, right? So first, this slide I stole from 1090. I haven't really put anywhere. So let's say we were doing 1090 for a minute. Suppose I had a propositional statement like this, and I wanted to prove something about it, right? I might want to prove that it was satisfiable, i.e. there's the setting of the variables, right? P to true and Q to false, such that it was true, right? Or I might want to prove that it was a tautology. How would I do that? I would have to prove for every setting of the variables it was true, right? So now the point is, how do you prove that it is satisfiable? Well, so here's various examples, right? How would I prove that this thing is satisfiable? Well, I would just have to give one assignment and show you that for that assignment it's true, right? Everybody buy that? I prove that this is satisfiable by giving you an assignment. How do I prove that it's not satisfiable? I prove it's not satisfiable by I have to list every assignment. There are 2 to the n assignments, and for every assignment, it's false, right? So how do I prove that some sentence is a tautology? Well, I have to prove that for every assignment, the left side is true if and only if the right side is true, right? For every assignment, the thing is true. Now, how do I prove something is not a tautology? Well, I just give one assignment in which it's false. Everybody get that? And what is the point of this? The point of this is the size of the proof, right? In the first case, I just gave one assignment. So the proof is order n size, meaning it's about the size of the sentence that I'm trying to prove. However, for the second case, if I have n variables, then the size of the proof is 2 to the n, because that's the number of assignments there are. In the third case, it's 2 to the n. In the fourth case, it's small. It's order of n size, right? So there's a different size in proof here. And that's kind of what the whole topic is we're talking about here, is how hard is it? So then another question is, the size of the proof might be small, but how hard is it for me to find that proof? All right, so here we have various classes of, right? There's polytime versus non-deterministic polytime. And for polytime problems, like, is my circuit satisfiable? There's a small proof that it's yes, but if you have to find it, it could take you exponential time. And so same for the negation of the problem. Anyway, so here, that's my father, and that's me. And one of the things my father started was this whole idea of, well, is there likely a small proof that something is not satisfiable? And the statement is, we believe there's not likely a small proof. Anyway, let's go back to here we had the halting problem is undecidable. Here we have things that can be done in exponential time versus polytime. My father was into whether things were exponential time or polytime. And then Steve Cook, I've written a couple papers with him. He was a professor at U of T when I was there. It has him as being older than my father, but that's because that's the picture I have of him. They're actually the same age. So what is this class, non-deterministic polytime? It's the class where if you have a fairy godmother to help you find it, then there's a polytime, there's a short proof that the answer is yes. but it may take you exponential time to find it. So here, circuit sat. So given a circuit, does it have a satisfying assignment? Well, to prove that it's satisfiable, you just need one assignment. But to find that assignment could take you exponential time, right? And so the question, so you can do it in exponential time, right? You just try all assignments. But the question is, maybe you could do, maybe there's a polytime algorithm, and we don't think there is. All right. And another thing that Cook did was he proved that satisfiability of circuits is at least as hard as every problem in NP. So if you had a fast algorithm for satisfiability, then you would have a class for every problem in this class, which in some ways would be great because industry has all these problems it wants to be solved. And one way it would be absolutely horrific because then we would have no cryptography anymore. Everybody could break into your bank account.
Oh, sir?
Yep.
Would a program trying to figure out someone's password be considered NP?
It would be an NP problem because if the fairy godmother gave you the password, then you could check really fast that it was the password. But to find the password, you have to try all passwords. And so the best algorithm for that is to try them all.
Okay. Is this why that, say for example, like you type in your password into like a program or whatever, say like you're trying to log into your bank account and they only give you like a certain amount of tries and
right.
then they lock you out?
Right.
Oh,
because they don't want people to try them all.
Okay. If they let people try them all, then obviously you'll be able to like get in after.
No, even then, if you had a really good password, a random password, then it would take exponential time to find it. If you had a really easy password, then in a small number of tries, they might guess it, right? They would start with your names of your girlfriends, and then the names of your pets, and the name of your mother, and your birth date, right? So if your girlfriend, for example, had all day, and she could try 100 things, she might be able to guess your password, right? Because you're not having a random password. All right, so
Professor.
Yeah.
Sorry, just a quick follow-up. So would we say that most NP hard problems are also in non-deterministic polynomial time?
Yeah, NP hard. Oh, NP hard, you mean? NP
Yes.
hard means that they're harder than NP. And so the halting problem is NP hard. It's harder than NP, but it's not.
Gotcha.
It's not an NP. So to be NP complete, it has to be NNP and NP hard.
I see. So NP hard would be hard to guess and hard to check?
Yeah, NP hard would mean if you could solve the halting problem, you could definitely solve the password problem, right? That was on the test.
Yes. Yeah.
So a halting problem is definitely NP hard, but it's way harder, so it's not an NP.
Okay. Gotcha.
Right? If you could solve SAT, you couldn't solve the halting problem.
So then I guess to rephrase, it would be NP complete problems usually are NP deterministic.
No.
Okay.
Right. By definition,
yeah,
NP complete problems need to be an NP.
Okay. I think I got that.
Yeah.
Thank you.
All right. So let's just review in case you don't remember. What's the definition of a problem being in polytime? It's there exists an algorithm, right? If a problem is computable, then there's an algorithm that computes it. And there's some constant C. So maybe C is 2 or 5 or 10. And then for every input, the algorithm that you've chosen, the fixed algorithm that you've chosen will give the right answer. And the running time will be bounded by the size of the input raised to the power of C that you gave at the beginning. Right? So it has to be a fixed C that doesn't depend on the input. Remember, if you've taken 1090, at least from me, you'll know that in the game, we say there exists an algorithm, there exists a C. So those are fixed. And then the adversary comes up with the input that doesn't depend on the C. So there's one C that works for every input, right? And what about non-determinism polytime? Well, for each instance, here the input is I, then there's going to be an exponential number of possible solutions to it, right? So if I is circuit satisfiability, then there's an exponential number of possible assignments, and each assignment is either valid or not. For example, a solution is an assignment. It either satisfies the circuit or it doesn't satisfy the circuit, right? And what is our goal? Our goal is, given an input, we say yes if it has a valid solution, and we say no if it doesn't. What did I mean by sufficiently high value? Well, maybe I'm trying to optimize something. So I'm looking for an optimal solution. A solution has a value. And so I'll say, does there exist a solution that's valid and whose value is at least 1 million, right? Or no, there doesn't exist such a solution, right? That's our NP problem, right? And in the official version of this, the algorithm doesn't have to give you the solution. It just has to tell you whether it exists or not. And so the other piece of this is that there's a polytime tester. There's an easy to run program, which is if I give you the input and I give you the solution, it's easy to test whether or not the solution is valid for the input. Right? So if I have a circuit and you give me an assignment, I can check, does that assignment satisfy the circuit or not? And so here's some examples. You haven't learned network flows yet, but there's some input like a graph and a K, and I can ask, does the graph have a flow of some certain value K? Either yes or no, right? So those network flows in polytime. So given a graph, I can find the best flow, right? And I can determine, is the best flow, is its value greater than K or not? But here's another question, is circuit satisfiability. The input is a circuit and a solution is an assignment. And a solution is a yes instance. If it has an assignment, a satisfying assignment is one that you plug it in and you get yes at the bottom. You get 1 out of at the bottom, true. You know, and so then the question of given an input, given an input and a solution, it's easy to see if it satisfies it, right? You just plug it in, and so the question we're asking is, given an input, does there exist a solution that satisfies it? See here at the bottom, we have this tester valid, and our problem, SAT problem, is given an input I, does there exist a solution which is a good solution for input I? Right, so that's just what we just said. This is just a little bit about non-deterministic Turing machines, right? We talked about, in the class, we talked about non-deterministic finite automatas. But here, what is a non-deterministic Turing machine? Well, it's the same as a deterministic one, except that it's not deterministic, right? A deterministic one says, given the character I'm looking at, I have a tape and I have a head for a Turing machine. And given I'm in a particular state and I'm looking at a particular character, it tells me what state I will be in next and what character to write and whether to move the head right or left, right? But here, a non-deterministic one, there's a set of possible things it might do. There are a number of paths that the algorithm might follow. And we say that a non-deterministic machine will accept an input if there exists a computation that accepts. And so basically, what would that computation be is you guess the solution and then check to make sure the solution works, right? So the way I think about it is, given a yes instance, suppose your boss gives you a circuit and you want to know whether it's satisfiable, and he wants to know whether it's satisfiable. So you take your input home to your fairy godmother, and if it's an yes instance, she can provide you a small solution, a witness, a proof, S, that will prove that yes, I is a yes instance. And you take this solution back to your boss, and your boss doesn't need to know how you came up with the solution. He can check that yes, the solution verifies that the yes instance, right? If your fairy godmother gives you a satisfying assignment to a circuit, then your boss can check that yes, the assignment that you have satisfies the circuit, right? But the dark side is if your boss gives you an instance that's a no instance, then even if you have a fairy godmother, there's nothing she can give you to convince you that it's not satisfiable. There's no way really she can help you. CoMP is the same, except we reverse the yes and the no. Let's not get into that too much. So here's, I guess this is a question. I put a number of tests and everybody got it wrong. Here, satisfiability is, it's a yes instance if there exists a solution for which the circuit, which there exists a solution for which it's a yes solution, right? So that's satisfiability. Co-satisfiability is, it's all circuits for which every solution is a false, right? And here's the question I've asked on tests. What about this problem, right? Given a circuit, I want to know, does there exist a solution for which the circuit says false? Well, now the question is this in NP or is it in CoNP? And it turns out that it's in NP because there is a witness. It's a yes instance if there exists a solution. And so the fairy godmother can give you that witness that it's a yes instance. But if you didn't quite get that, that won't be on the test. All right, so here's just, we did, if the problem actually can be solved in polytime, then you don't need a fairy godmother. The whole thing's in polytime, right? So this is just saying, if given any problem that's in polytime, it's also in NP. Why? Because the fairy godmother can help you. All right, so here's another question. If a problem is in P, then one of the points of it is that the size of your solution can't be bigger than some polynomial in the size of your input, right? So let's say n is the size of your input, then the solution can't be bigger than n to the 1,000. Why? Because if the fairy godmother gave you a solution, you need to be able to check it in polytime, right? So your solution can't be can't be bigger than a polynomial, and hence an algorithm is you could try all possible solutions in time exponential in the size of the solution, right? If the solution has 2 to the 1,000 bits in it, then in 2 to that, you can try all solutions, right? And that's why if a problem's in NP, then you can do it in exponential time. This is more than I planned on teaching today. I just started going here. Anyway, let's go through all this sort of stuff. Oh, this is just saying what somebody asked just a minute ago, right? If I have a problem that's in NP, then I know it's not too hard. It lives down here. If I tell you that it's NP, right? And if I tell you that it's NP hard, then it lives up there. And NP complete is you're in the middle, right? That you that you're in NP, but you're hard as everybody in NP. And Cook showed that SAT is as hard as everybody in NP. So in order, what you need to do, if you have a new problem, you just have to show it's as hard as SAT. Right, so you take, what do you have to, if you had to on a test show that a problem was NP complete, you would have to show that it was an NP, meaning a small witness would help you, and you have to prove that it's NP hard, meaning if you could solve it, you could solve everybody in SAT. All right, I'm kind of going fast here, but these are just definitions it would be nice for you to have in your brain somewhere. All right, so now let's think about this a little bit more informally, right? Everybody in industry wants a free lunch, right? They want to be able to solve hard problems easily, right? So for example, here's an example problem. I give you a description of what I mean by a good plane. I tell you what kind of lift I want, how many people it's going to hold, the cost of it. I don't know. I tell you various things. And you might want, then the program is going to automatically find how to build a plane that has that description, right? So basically, as I tell you the requirements of the plane, can it automatically discover how to meet those requirements? That's basically your classic NP problem. I tell you a requirement of the solution we're looking for, and then and if I gave you a solution, you could test, does it have the right requirements? But finding the solution could take you exponential time to search them all. And right, industry wants to be able to solve that. Here's another problem, is given a circuit, does it have a satisfying assignment? Given a graph, does it have a 3 coloring? We'll talk in a minute about what a 3 coloring means. I could give you, you might not know this. You know, York might have a really bad schedule. You say, why is it scheduling this so bad? But here's the computational problem, is I tell you what course everybody wants to take. I tell you some requirements on those courses, and it's NP complete to find an optimal schedule. All right. So what we're going to prove right in the next couple of slides is that these two problems are equivalent. If you can schedule, then you can graph color, and if you can graph color, you can schedule. And this one here is kind of the definition of a free lunch. I want to be able to do things like that with a free lunch. Well, one of the things that Cook proves, and maybe we'll do it today, is that if you had an algorithm for satisfiability, then you can solve every problem in NP. And what I would like to show today, because I think it's a lot of fun, is proving that if I had an algorithm for graph coloring, then I could have an algorithm for circuit satisfiability, right? And so what's the reality here, however? The reality is there's likely not a way to get a free lunch. So you likely can't solve the airplane problem. So you likely can't solve the circuit problem. So you likely can't solve the graph coloring problem in polytime. And so you can't solve scheduling in polytime, right? Do people kind of follow that? That's what we're trying to prove. We're trying to prove that all these problems are hard. And how do we prove that they're hard? We prove that if you could do this one, 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 you could do them all, right? But likely you go the contrapositive, likely all of them are hard.
But yeah, for these algorithms, the fastest we have right now to solve them is just probabilistic algorithms, right? Or
we're not talking probability here at all. I doubt that if you brought probability in it would help. Do you mean non-determinism?
Yeah, I was just thinking, like, when you have these problems where randomly, like if you want to crack somebody's password or guess the solution to a satisfiability problem, is it just better to just keep on making random guesses, and then like since we don't have a
Well, it depends on sort of the distribution. I'm going to assume that there are an exponential number of possible passwords and only a very small number of them. In fact, for a password, only one of them will work. So if you randomly choose a password, the probability that it works is exponentially small. And so it's going to take you exponential time,
gotcha.
right?
Oh, Jeff,
Yeah.
when you say that it's hard, does it mean so hard? Your definition of hard doesn't mean like we're able to solve the problems or we are unable to solve the problems.
Oh, yeah. So hard here, good question. By hard, I mean, can I do it in poly time, right? Clearly, I can solve all of these problems. Well, what I showed before is that all of these guys have poly-size witnesses. So in exponential time, I can try them all. So the question, but exponential time, 2 to the 100, right? If my witness is of size 100 and I want to try them all, then there are 2 to the 100 possibilities. And 2 to the 100 is bigger than the size of the universe. So it's just not practical to try them all. Right? Does that make sense?
Okay. Yes. Thank you.
So, I mean, is there a practical algorithm that will finish today? Not finish at the end of the universe.
So, sir, how did it lead up to like would love a free lunch? That's what I'm confused about. So
Oh,
are
that
we just okay?
The airplane problem is sort of, I'm just saying, it's a classic industry problem. I'm not even defining what it is. You can imagine I'm in industry and I'm looking for a solution to my problem, right? So how do I do that? I write down the requirements on the solution, right? I say, oh, what does it mean to have a solution? Well, what does it mean to have a good airplane? Well, it needs to fly, right? It needs to fly fast. It needs to be cheap. It needs to be light. It needs to hold all my people in it, right? So I write down a description of what I need. And I do it in such a way, if some real hotshot employee came and gave me a solution, then I could say, yes, it meets all the requirements of my solution, right? I've stated what my requirements are. So if you give me something that meets those requirements, then we will be very, very happy, right? So it's kind of like a circuit. The circuit will represent the requirements, and you plug in the solution and the circuit will tell me, is it a good solution or is it a bad solution, right? Mm-hmm. So now what's the free lunch is, can I find my solution automatically? If I tell you what I want in a solution, can I for free get a solution that satisfies it? And so that's what I mean by a free lunch. And how does that relate to circuit satisfiability is I give you the circuit telling me what I require of the solution, and then can I find a solution that will satisfy that circuit? And the big red X means we do not believe there's a polytime algorithm that will do that. So we will not get a free lunch.
Okay.
Right?
And are we going to talk about the biochromatic, the graph and the course description stuff later as well? Okay.
Yeah, what we'll see how we're doing for time. This one is really fast. Actually, this one is pretty fast too. I think we can do all of these right now.
Okay.
They're all surprisingly easy, and it'll give you a flavor for what we're talking about here.
Okay.
Jeff,
thank you.
Jeff, is this basically an optimization problem, like the traveling salesman problem?
Traveling salesman problem is also NP complete. The only difference is traveling salesman is asking for an optimal solution. That means different solutions will have different values, right? Well, here we're doing a yes-no thing, right? In the yes-no case, either it's a good solution or it's not a good solution. So if we wanted to do traveling salesman problem, we would add the extra constraint that does there exist a solution to traveling salesman problem whose value is at least $1 million, right? That turns it into a yes or no question,
Makes sense.
right? So here we're just talking about yes, no questions, but everything we could say here could also be said for optimizing, right? For circuit, for scheduling, you could say, I want the best schedule, or then I could just say, is there a schedule, right? So, right, I could say, give me the schedule that has the fewest conflicts, or is there a schedule with no conflicts, right? Those are two. One is an optimization and one's a yes, no. All right, so I think we did this already. There are a bunch of instances. Each instance has an exponentially large set of solutions. Some solutions are valid and some aren't, and it's given a solution, it's easy to tell whether it's valid or not, and our goal is to find a valid solution. All right, in all of these problems, right, there's a large search space, and only a tiny fraction of that search space will work, and brute force to try them all takes too long, and we have no feasible algorithm for it. But if we had a feasible algorithm, no feasible algorithm is known. No polytime algorithm is known. But if we had a polytime algorithm for one, then we could solve all of these in polytime.
So what do you mean by brute force?
Brute force is you try all exponentially many solutions and see if you can find one that works.
Okay.
Right? All right, so here, let's make this more concrete, right? All of that, you might not have followed any of that, but let's make it concrete, right? So you work for York University, and you know you have a set of courses. You know for each course, for each student, what courses they want. You have what time slots are available. You know what professors are teaching what courses. And what is a conflict? A conflict is if a professor or a student wants to take two different courses and they're taught at the same time, then that's a problem, right? I can't, right? So one right? Everybody understand the problem, right? Is we want to schedule, we'll go into it again. This was just a quick definition, but the point is to allocate every course to a time slot to have as few, to not have conflicts, right? And what is a conflict? The same student wants two courses that are scheduled at the same time, right? All right, so how could what's the brute force, right? The perspiration search is you try all possible schedules, but there are an exponential number of them, right? Meaning if we had 50 courses, then suddenly the number of schedules is more than the number of atoms in the entire universe, all right? Is there a fast algorithm? We don't know. We don't think there's a fast algorithm. We don't have a fast algorithm. We can't prove there's not a fast algorithm, all right? It's one of the biggest open questions in the field. Can you schedule faster than brute force, right? Because if you could schedule faster, then you could do all of these problems faster, and that would be exciting. All right, so here's a different problem. We have a graph. You know, graphs are nodes with edges between them, right? They might be cities and roads, or they might be people and the friendship network. They might be computers and wires between them. And what we want to do is find what is called a bichromatic coloring. What does that mean? It means you color every node with as few colors as possible. And the bichromatic comes from every edge, right? Here's an edge of the graph. And you'll note its two nodes have different colors. That's bichromatic, two colors, right? Every edge has two different colors, right? You look at every pair of edge, right? These two nodes have the same color, but that's not a problem because there's not an edge between them, right? And I might ask, give me the minimal number of colors I need to be able to do this. Or I might ask, can I do it with 3 colors? And it turns out that to knowing whether I can do it with 2 colors is polytime, but to know whether I can do it with 3 colors is NP complete. So one possibility is you just try all possible colorings, but again, the number of colorings is exponential, and we don't think there's a good algorithm for this. All right, so now let's do a quick reduction between these. Now, in this case, I'm not only am I going to do a reduction, I'm going to tell you that these problems really, really are the same. And why is this useful to you? All right. It's useful to you because when you get hired out in the world and your boss comes to you and asks you to do some brand new problem that you've never seen before, right? Then you can say to your boss, boss, that really feels to me like graph coloring, or that really feels to me like course scheduling. And I know those have no fast algorithms. So hence, I really don't believe your problem has a fast algorithm. And it's good to be able to say to your boss, hey, the problem that you want me to solve is NP complete, because then that lowers the expectations of what your boss is going to ask you to do. He's not going to suddenly ask you to come up with an algorithm that always gives you the optimal solution, because he knows there's likely not an algorithm that can do that. All right? So that's why we're going to talk about comparing 2 problems, right? They look, cosmetically, they look differently. One is coloring the nodes of a graph. One is scheduling courses. They look different, right? But here, I'm going to show you how fundamentally these 2 problems are identical, all right? So why is that? Well, what is our action? Our action is to schedule, right? And here our action is to color, right? Those are our verbs. And what does it mean to schedule? What are we're scheduling courses to time slots, right? What does the scheduling mean? It means to take each course and assign it to a time slot. What does color mean? Color means to take each node and allocate it a color, right? So in some ways, there's a mapping between courses, which we want to give time slots, and nodes of your graph, which we want to give colors. So here in our mapping, we're going to say every course will get a node of your graph, or every node of your graph will be thought of as a course. All right, see, we have the connection there already. All right, and now, what are we acting with? Well, that's where it's the time slot, right? We want to allocate to every course, we want to allocate a time slot. And to every node, we want to allocate a color. So there's a connection between time slots and colors, all right? So I might say 1 o'clock on Monday is blue, right? While 3 o'clock on Friday is green, right? Every time slot is associated with the color. Every color is associated with the time slot, right? Does that make sense? And then we have,
Yes.
yeah.
I was just confirming.
Yeah, and then we have the issue of what are our requirements? Our requirement is that they can't conflict. What does that mean, can't conflict? That means, let's put an edge here, right? We'll put an edge between one course and another course if some student or the professor is teaching them or wants to take both of them. And what will that tell us? That would tell us that they can't, if they're taught by the same people or taken by the same people, then they can't be at the same time slot. Well, over here, if there's an edge between them, then you can't give them the same color. right? So you see how this is exactly the same problem. I have a graph with edges between them, and I need to allocate the nodes colors so that each edge has 2 different colors, or or my nodes are courses, and I have to give each course a time slot such that if there's an edge between the courses, then they can't be given the same time slot. So that just says the problems are the same. Does that make sense?
Yes.
It does.
Are there different ways to map these problems? And how do you know if you have the best possible mapping?
Well, in this one, I'm pretty sure that this is a pretty straightforward, obvious mapping.
Right.
And there probably are other mappings, and don't know.
Right. Okay.
It's an art. Finding mappings is an art. All right, so now what did we mean by if you could solve one fast, you could solve the other fast? Well, suppose I had an algorithm that could solve the coloring fast. Then I'm going to design an algorithm that can solve scheduling fast. How? And that's going to prove that the scheduling problem is somehow easier than the coloring problem, right? Because if I could color, I could schedule, right? And how do I do it? Well, I give courses and whether they conflict, and I form a graph. And then I know my Oracle tells me whether or not I can color, and that tells me whether or not I can schedule, right? Does that make sense?
Now, Jeff, I think there's a problem with the courses, right? Like last semester, like they didn't allocate enough spaces for students in these courses. So guessing the correct amount of students for a course, is that like a similar problem to scheduling or coloring too?
Yeah, that's what these are all problems, right? Well, I mean, the one problem is when I'm scheduling the courses, I have to know, is there going to be somebody who takes basket weaving and takes Jeff's algorithms class, right? They're going to hope that nobody will take both of them, and so they'll schedule them at the same time. And then suddenly you want to take both of them, so you have a conflict, right? So,
and since we're doing like when you're making these schedules, you also have a list of students, right, who want to take these courses. So when you have these multiple parameters, does that sometimes help the problem, like make it a little bit easier? Because if you have
more constraints, the harder it is going to be to satisfy them.
I meant like in terms of like since you know that these many students are for sure going to take this many courses, so it's like you don't have to like you kind of know some things at least.
Yeah.
That's what
for sure. So they do have heuristics which work, right? In fact, the way it works is computer science department says, let's schedule the required courses so everybody in third year can do okay. And they don't talk to the people in psychology at all, right? So if your course, computer science conflicts with with psychology, then just nobody has considered or cared about that.
Gotcha.
All right, so how do you go the other direction, right? We say, suppose we had an algorithm for the Oracle problem, how would we solve coloring? Well, we would do it the other way. If we were given a graph that we wanted to color, we would map it over to courses and conflicts, and then the Oracle would tell us how to schedule it, which would tell us how to color the graph, right? So that shows if you could do one, you could do the other.
Professor?
Yep.
Do you mind explaining again how we can use 3 colors to map more than 3 course conflicts?
Oh. You know, I think I skipped over that. So up here, I was saying that it's NP complete to know whether or not you could do it with 3 colors. But the more general problem is, give me the minimal number of colors in which I could do it, right? Or could I do it with 1,000 colors, right?
Gotcha.
So down here, what we're mapping it to is, we don't have 3 colors. We have a color for every time slot.
Okay, that makes sense.
That was a good. I definitely wasn't clear about that. All right, everybody kind of get that? All right.
Yes, sir.
So let's in 5 minutes do the thing that made Cook famous. And it's like everything in hindsight looks trivially easy. So we're going to say, look, it's trivially easy, right? So here's what's the circuit satisfiability problem, all right? You're given a circuit, which is AND, ORs, and NOTs. He particularly didn't look at general circuits. He looked at clauses, ANDs of clauses, where each clause was the OR of 3 literals. So he looked at specific types of circuits, but we'll be more general here. And then there are variables, right? And the question is, given an assignment, right, you can have the true false percolate down, and you find out whether this assignment satisfies the circuit or not, right? And our goal is, here's another assignment. You percolate it down. It does satisfy the circuit, right? So given the circuit, we want to know, is there a satisfying assignment, right? That's the circuit satisfiability problem, right? And our belief is that, so one option is to try all possible assignments, but again, the number of them is bigger than the number of atoms in the universe. So, and we don't know a faster way of doing it. Well, I mean, what do you do in practice? Actually, in practice, what you do is you do Davis-Putnam, which is if you took 1090 from me, you would have learned Davis-Putnam. And in practice, it works pretty well. All right, so what's the input, right? The input's a circuit, and the solution is an assignment that tells you, right? A solution is assignment to the circuit, and given an assignment, we can quickly test to see whether the assignment satisfies or not. That's just going to the formal definition of right? So I want to prove that if you can solve the circuit problem, you can solve any problem in an NP, all right? So to make that more concrete, I'm going to show you how to solve the airplane problem, all right? What's the airplane problem? Is I have an input that specifies all the requirements on the airplane. What's the cost, the efficiency, da-da-da-da. What do I need for my airplane, right? And what is a solution? A solution tells you how to actually build it, right? And I'm going to assume that if somebody gave me a solution, I could test whether or not it was a good solution. So I have a program called valid subplane, and that program runs in polytime, and maybe that program is written in Java. And what do you give to the program? You give it the description of what we need for the airplane. You give it a solution, how to build the airplane, and valid tells you whether or not this is a good solution to that problem, to that instance, right? Everybody here get what we're doing here? Right? And what is our goal? Our goal is to given the input, which tells us the description of what we need, the requirements on the airplane. Our goal is to find a way to build it. Free lunch would be, I quickly can find how to build this thing, right? Or to prove that there's no possible solution, right? That's what I want to do fast. I want to know, given my requirements, can I build it? And if so, how do I build it? All right, so I'm going to prove to you that, right, so what is this problem? Is given an input, does there exist a solution for which my program, my Java program says yes? All right, so I'm going to prove that if I can solve circuit satisfiability, then I can solve this airplane problem. All right, we're going to do it really quick. 2 or 3 slides. Well, if you can do it by a Java program, then you can do it by a Turing machine. And I'm not going to show you how, but you can imagine if you can do it by a Java program, you can do it by a circuit. Why? Well, what do I have in front of me as a laptop? And what is this laptop? It's a thing that runs Java programs, and it's made out of AND gates and OR gates. So I can take this Java program and I can convert it into a circuit, right? And the circuit has an input I and an input S as bits, and it outputs yes or no, whether the solution satisfies this input. All right?
Professor?
Yeah.
I have a question about the circuit.
Yeah.
So are we just talking about just an arbitrary circuit, or would you be giving us like a specific circuit that does specifically something?
Are you talking about what will be on the test?
No, I mean, in general, what you mean by circuit.
So a circuit is a gate. It has and or not gates, and they come down and they have wires at the top, and they have a yes no wire at the bottom. And I'm talking about if you give me a Java program. We say we have this polytime Java program called valid, and I can convert that Java program into a circuit that does the same thing.
I see.
Right? You can believe that anything a Java program can do, a circuit can do.
Okay, so we're just talking about a random circuit then.
No, it's not a random circuit. It's the circuit that computes this airplane problem.
Okay, I get it. Okay.
Right.
All right, thank you.
So
I have a question kind of related to what she was asking.
Yeah.
So kind of like, I've forgotten if it was this course or 1090. You said that you changed circuit to assignment and input rather to assignment.
Yeah.
Is it kind of like, I don't know, the input kind of like the assignment?
Here we're just talking about the circuit. Yeah, certainly a circuit takes a solution as input, right? But here the circuit is the input to my problem. And an assignment is the solution to my problem.
Okay.
Right?
Thank you.
All right, excellent. So here are two problems. And I'm going to prove that if you can solve circuit satisfiability, then you can solve the airplane problem. And how do we do it? But on the other hand, you likely can't do any of these, right? This is just by contradiction. You likely can't do the airplane problem, so you likely can't do circuit, right? So here, how do we do the reduction? We have to do an instant map. We have to take an input to the airplane problem and map it over to an input to the circuit problem, right? And how do we do that, right? All right, so I'm given the requirements of the airplane, right? And I want to find how to build the airplane. So what do? What can I give my oracle? My oracle, I give it a circuit, right? And it tells me whether or not it's satisfiable. So what circuit do I give the oracle? Well, I had a Java program that could tell me whether an airplane was tell me about airplanes, and I converted it over to a circuit. And then I took that circuit and I took the airplane requirements that I have and I plugged them in here, right? And so now this is a circuit that is satisfiable, right? What will satisfy this is a solution to the airplane problem, right? You kind of follow this as I just build up a circuit to what am I looking for? I'm looking for a solution that will satisfy the circuit. I'm looking for a way to build an airplane that satisfies the requirements. And that's it. That's the entire proof. Do you kind of get it? Right, right? This problem here, I'm given the description of an airplane and I want to find a solution such that if I plugged it into the Java program would say yes. So we just convert the Java program into a circuit. And then we ask the circuit, hey, is there a solution S that if I plug it in this circuit, I get yes? Well, what is that solution? That solution is a description of it tells me how to build the airplane. All right, that's all I...
So this works if we can create a one-to-one mapping between the two problems?
Yeah, they don't have to be one-to-one mappings. We talked about, I mean, in our various homeworks, they weren't necessarily one-to-one mappings. Anyway, let's give another example here. All right, here's the this is what I wanted to do today. All right, so we're going to show that if you have an algorithm for solving 3 coloring, then I'll give you an algorithm for solving the circuit satisfiability problem. All right, so what are we doing? I'm given a circuit and I want to know, is it satisfiable? Here I said circuit, that's the same as circuit satisfiability. Right, so what do I have to do? Given my circuit, I have to build a graph that I give to my oracle, right? Because my oracle, I give my oracle a graph, and the oracle will tell me whether or not it has a 3 coloring, right? And how do I get that graph? Well, I'm going to build it from, I'm going to take the gates of my circuit, and then I'm going to, for each gate, I'm going to have a gadget. And then I'm going to build those gadgets. I'm going to build some weird graph. And then I'm going to give that weird graph to my oracle. And the oracle will tell me whether it's colorable or not. And that will tell me whether or not my circuit is satisfiable or not. Right? Does that make sense? So let's see how we're going to map between them. Right? What is an input to the circuit problem? Is the circuit of gates. So what's the input to the 3 coloring? It's a graph. So what do I have to do? I have to take a circuit of gates and I have to map it over to a graph, right? Given a circuit of gates, I have to form a graph. And then what is the solution to the circuit problem? Well, it assigns a true false to every input variable, right? And so what do I need? Over here for the graph problem, it assigns to each node either green, red, or blue. Actually, in some places, it's green, red, or brown. I'm not consistent what the 3rd color is. All right? So what are we going to map? We're going to say true. Well, true feels like green to me. And false seems like red to me, right? And blue's going to be our 3rd color, right? Sometimes it'll be blue, sometimes it'll be brown. It's our 3rd color, right? So now, what is a variable over here? Well, here we're assigning true, false to each variable. So here we're assigning red, green to each node. So clearly, every variable is going to get mapped over to a node of our graph, right? And more than that, here our circuit, not only does it have these input wires, but it has all these internal wires. It has that wire there and that wire and the output wire, right? So each of those wires is going to be mapped with true, false. So each of those internal wires is also going to be mapped to a node. All right? So you might not be following what I'm saying so well. Oh, so now what is a gate going to get mapped to? A gate is a connection between these wires, and a gate will be a gadget composed of nodes and edges. All right, so when I was a graduate student at U of T, Stephen Rudish was a postdoc. And while I was there, he came up with this gadget. He wanted a gadget with certain conditions, and he did a computer search, and he found this gadget. And this gadget is, we're going to see what it does, right? It's a gadget. And so I can ask, can you color it with 2 colors? Can you color it with 2 colors? No. Well, there's a triangle here, right? And the triangle needs 3 different colors, right? So you're going to need at least 3 different colors, so you can't color it with 2 colors. Can you color it with 3 colors? Yeah. Here's a question I often ask. How do you know you can color it with 3 colors? Well, I give you a 3 coloring, right? So a 3 coloring is a proof I can color it with 3 colors, right? Everybody follow? I have this gadget. I can color it with 3 colors. So now I want to convince you that this gadget acts like an OR gate. Why is that? Well, an OR gate has 2 input wires and 1 output wire. So my graph has this node up here is going to be called the X input, and this node over here is going to be called the Y input, and the output, and this node down here is going to be called the output. All right? And we need a map true to green and false to red. And yeah, we have the third color who keeps changing what its color is. Right? So this palette up here is going to define what we consider to be the true color and the false color. So this node right there is going to be the node that we call the true node. Whatever you color that node, we'll call the true color. And whatever color you color this node, we'll call the false color. So here, true is the false color, and yellow is true is the red is the true color, and yellow is the false color, right? But we can recolor everything, right? We can just rotate the 3 colors. So we might, without loss of generality, we can assume that this node is colored green and this node is colored red. All right? So for our sake, green will be our true color and false will be and red will be our false color, right? Does that make sense? All right, so now we're going to see how does this thing compute? Well, what does an OR gate need to do? False, false has to give you false. And everything, if any of the inputs are true, you have to get a true output, right? That's what a false does, right? That's what an OR gate does, right? Everybody buy that? So let's think about how it computes. Let's look at false, false. If the input is false, false, then that means this node is colored false and this node is colored false, right? And so then we say of all coloring, suppose I had hundreds of people color this graph. Well, my bet is about a quarter of you will color this node false and this node false, because you'll do it kind of randomly. And then it will follow, what color is that color? It turns out that that color has to be false, all right? And so that's how it's computing, false, false, this has to be false. And similarly, if this is false, true, any proper coloring where this is false and this is true has to give a true there. And similarly, true, false, any coloring that's true has to have a true there. And similarly, true, true, this has to be a true there, right? So in some ways, this coloring is computing the OR gate. Does that make sense?
Yep. Yeah, I'm just
So
confused about the third node there.
the third color, this one here?
Yeah. So I'm just confused about what the role for that is. Like, if
All
you
right,
have
well,
a-
maybe I'll show you right now. All right, here's an example. Here's an example of a proof, all right? Suppose I want to prove to you that if this is false and this is true, then this node has to be true, all right? So let's go through the proof, right? We want to say, what does this node have to be, right? That's here, this is true and this is false, and this is the third color. So what color can this be? Well, it can't be false and it can't be true, right? It can't be false because this edge has to be bichromatic. It can't be true because this edge has to be bichromatic. So what can this node be? It has to be the third color, right? Does that make sense?
Yep, gotcha.
Now, what does this node have to be? It can't be the third color and it can't be false. So it has to be true, right? Now, what about this node here? It can't be the third color and it can't be true. So it has to be false, right? And what about this node down here? It can't be the third color and it can't be false. so it has to be true. So that proved that example. Does that make sense? And you can see how we use the third color, right? So do I have oh, I don't have another one. Sometimes if you look later on the slides, I have more of these proofs, but they're about the same. All right, so here's another gadget. It's going to have the same, we'll call this the palette. The true color, the false color, the third color, that will be the same for every gadget, right? And what does this gate do? I say it's a NOT gate. Why? Because if this is true, right, then what does this have to be? It can't be true and it can't be the third color, so it has to be false, right? And if this is false, then this can't be false and can't be the third color, so it has to be true, right? Does that make sense?
Wait, Jeff?
Yep.
How do you know which node is X and which node is output and which node is Y? Like,
well, because it's
us?
not an arbitrary graph. I'm building it.
Oh.
I'm building the graph, right? So remember somebody said, is there a bijection between these problems? No, it's not a bijection. I'm given a circuit and I get to build a graph. I'm not saying every graph will look like this. I'm saying I'm building the graph, right? So I get to build the graph. And let me tell you how to build the graph, all right? Here, this is what we're doing. I'm given a circuit and I want to know, is this circuit satisfiable or not, right? So what do? I have to build a graph that I give to my oracle. And that graph can be any graph I want to build, all right? So you're ready to see what the graph will look like? Here it comes. That's the graph, right? So it looks like a scary graph, but it's not so scary. Let's go through and understand what it does, right? Here we have an OR gate. So for an OR gate, I build the OR gadget. And what does an OR gadget have? It has a palette that's going to define true and false. And it's going to have an X node, and it's going to have a Y node, and it's going to have an output node, right? That's what my OR gadget is. Everybody agree with that?
Yep.
Then I have a NOT gate. So what's a NOT gate? Is I have the exact same palette. Every gate's going to have the same palette. And then this is a NOT gate, right? And the NOT gate, the NOT gadget, right? It has input Z, and it has some output node, right? And then, oops, where is it? Then I have an OR gate. And what does the OR gate? It has the same gadget, and it's an OR gadget, and it has a node, which is the input, and the input to this gate, right? The input to this OR is the output of that OR. So the input to this gadget is the same node as the output of that gadget, right? And the input, the right input to the OR gadget will be the output of the NOT gate. Why? Because the NOT gate's output is the same as the input to the OR, right? Because if this gate outputs true, then this gate is going to input true, right? So the true has to have one color. So there's one node that will be one color, which is the output of this circuit and the input of this gate, right? Does that make sense?
I don't understand, like, how do you know where the input is at? Like looking at this, right? How do you know where the input is and where the output is?
Well, I'm building the gate. I'm building this circuit, this graph, right? So
yeah.
Look back at this gadget, right? So memorize what that looks like, all right? It kind of looks like that, right? And memorize this, what it looks like. It's a triangle with two extra nodes, right? All right, so now I'm going to tell you how to build this circuit, right? You're going to say, oh, there's an OR gate. So I'm going to build the OR gadget. So let's do it here, right? So first I say I have an OR gate, right? I'm given this circuit, and I have to build the graph. So I have an OR gate, So I say, what does my OR gadget look like? Well, it looks like that. You might, if you memorized it, that's the OR gadget. In fact, I cut it and I pasted it right there, right? And what does an OR gadget have? An OR gadget has a palette, it has an X node, it has a Y node, 2 input nodes, and it has an output node, right? So I write those down on my paper. There's my gadget. Then I come over to the next gate. This gate is the NOT gate. So what does it look like? Well, it has the triangle, which is the palette, and the triangle will be the same triangle as my last, right? All of my gadgets will have the same triangle. So these 3 nodes are common. And then a NOT gate, you might remember a NOT gate has a triangle and it has 2 extra nodes, the input node and the output node, right? So here we built.
So here you made them like, I'm just imagining like if I want to draw this, right?
Yeah.
What I do is I make them separate, then I combine them together. So I make X and Y separate, and then I make them not separate, and then when I combine them together, this is the final shape I'm gonna have, right? Just to visualize how this is made, because like if I want to make this like all of it together at one time, I just feel it's just too big, kind of.
Yeah, well, it's big, but it's not that big. You could certainly build it. You could certainly write a program which would output this graph.
Yeah, like I do know how the NOT shape looks like, so like I can just put it on the side. I do know how X looks like.
Yeah. The NOT looks like NOT looks like that.
Exactly. So now
I put one. I put one. There it is, right?
Okay.
And now this OR gate here, what do I do with the OR gate? Well, the OR gate is another OR gadget. So here you can see it. That's an OR gadget, and it has the same triangle.
Yeah, I
right?
see. Okay.
Right? That's just, it's an OR gadget with the triangle moved up there.
Yeah, exactly.
Right? And what are its inputs? Well, the input to this OR gate is the output of that OR gate and the output of that NOT gate. So the input to this OR gate is the same node as the output of this gadget. And this node is the same node as the output of the OR, of the NOT, right? And then what's our total output? Well, it's this OR's output is the total output. So there it is. That's our total output, right?
So basically, the OR is the bridge that connects everything together.
Yeah, it's whatever your circuit here is. You build the graph, right?
Yeah, because the OR and the NOT. Okay, I see.
Yeah.
They go like right away to the OR, which is the final output.
Yeah.
Okay.
And you might ask, what about the AND gates? Well, if you know about 1, I could build a gadget for AND gates, but 2, I don't need to, because with De Morgan's law, you can get rid of all AND gates. All right, so that is what we did. And now let's see what these things do. Suppose I put a true, false, an assignment to this circuit, right? Well, let's put an equivalent. The assignment was X was false, so I make my X node red, right? The input X node red. And if Y is true, then I make the Y green, and Z is true, so I make the Z green, right? So I say, hey, do I have a coloring like this? Well, remember we proved, right? If this is false and this is true, then the OR has to give true, right? Well, we proved that if this was red and this was green, then the gadget has to give green. And similarly, a NOT gate, if this is true, then this has to be false. So similarly, if this green, this has to be red. And then this OR gate has a true here and a false here, so it has to give true. And so here we have green and we have red, so this has to be green. So this...
Professor?
Yeah?
I don't understand why the second OR gadget isn't connected to the output of the first OR gadget.
It is. That node, do you see my mouse?
Mm-hmm. Yes.
That is the output of the first OR gadget and the input of the second OR gadget.
So why is there a line being connected all the way to the top? To the third node?
That's because if you go back to see what the gadget looks like, right? It's it's this palette,
Mm-hmm.
right? So these nodes of the gadget, I'm always putting kind of together, but the palette, I move way up to the top because every gadget will have the same palette, right? So see these nodes here with the little triangle, the two lines in the triangle? If we come down here, see that's the two paths of the little triangle. That's the two paths of the little triangle. But we moved all their palettes up to the top.
So the question, I suppose, then, all the nodes that are connecting to the top palette,
right?
Then none of them can be yellow by default, right?
Right, exactly. Right. That's a very good point. And why? Because I want all my wires here to be true, false. So every value, you'll note that every input thing, right? This is an input output. It's connected to the third guy, and that keeps us from it being the third color. That keeps all our wires as being true, false.
Okay. I think I see. Thank you.
Right? We have one palette because we have one definition of true and one definition of false and the third color, and we make sure all our inputs are connected to the third color so that none of them can have the third color.
Sir, I have a question.
Yeah.
So I understand that when you change the colors for like red and green, you do say that this is true and this is false.
Right.
Like I have a suggestion here. Why we don't kind of like also change the color of the lines? Then it will be visually easier for us to see where are
the
they
lines.
connected. Yeah, exactly.
No, the lines don't have colors. The lines need to be bichromatic.
Oh, okay. I'm just like thinking personally, like if I make it like with colors, I can see exactly where each part is connected.
Well,
like,
here I guess I colored. Oh, here I could color the palette. I suppose I could color all those edges. But
I see. So we're not allowed to color the lines, right? Like make them.
The problem is the color that nodes.
Yeah, I see. Okay.
Right.
Yeah.
All right. So here we have 1 minute left, and we're going to finish in our 1 minute. All right. So you can see how the coloring percolates down, and what do we want? We want to know. Our question is, can you give me an assignment that outputs true? Right? So I want to force this output node to be the true color, right? How do I force it to be the true color? Well, it already, as somebody just observed, has an edge up to the third node, so it can't be the third color, right? And I'm going to add a new edge, and this edge goes from the output to the false color. And what does this edge tell me? That tells me that the output node cannot be the false color, so it has to be the true color, right? So let's get back to the big picture. Is I'm given this circuit, and I want to find a satisfying assignment. So I give this graph to the Oracle, and it will give me a coloring. And this node here guarantees that the output color is true. And this thing guarantees that whatever coloring he gives me here at the top will give me true at the bottom. All right? So this circuit is satisfiable if and only if the graph is 3 colorable. So given a circuit, I want to know, is it satisfiable? I map it over to this weird graph. The Oracle tells me whether the graph is colorable or not, and that tells me I can just read off, right? If it gives me a coloring, right? If it gives me a coloring here, I know, oh, this node is the false color, so X has to be false. This node is the true color, so Y has to be true. Right? Does that make sense?
Jeff.
Yes.
Those gadgets, are they also scalable to n bits, like n bit inputs, or is it just for?
It probably could be, but we don't need to, right? Because I'm assuming my gadget sorry, I'm assuming that my circuit is made up of binary ORs and binary ANDs and binary and a NOT, right? So you could think, well, I have an n-bit OR, but let's just build the n-bit OR out of a tree of binary ORs.
So in general, that's a faster way to do it than just having n-bit gates. You just split up into smaller.
I'm not sure whether it's faster or not. If I in terms of building gates, I'm not a circuit builder. I've never built a gate, but in terms of, we can think of a big OR gate is a tree of binary OR gates.
Gotcha. Thank you.
And that's it. That's it. We're done, guys. Right? Absolutely done. Any questions about that? Yeah.
Yeah. So for the second node in the OR gadget, first OR gadget, the second node on the right side,
the Y,
that's connected to both falses. No, here,
yeah.
So for the gadget of OR, first OR,
there we have the X,
node on the right
and we
side.
have the Y.
Yeah, the one below that. The one below Y. Yes, that's connected to both false.
Yeah. But we don't need to, well, we don't need to worry about that. We go over to the gadget, and that's the way the gadget's built. Right? Here are the two input nodes, and this node is connected to both of them.
So wasn't it a property that no three colors can be same in all three connected nodes?
Yeah, but that's what we're going to make sure that's the case. If that's where we said, if this was, when we said, remember we asked, what color does this have to be? Well, it can't be the true color and it can't be the false color. So it has to be the third color.
But it's also connected to the false, the third. It's connected to 4 nodes total, no?
Right, so it can't be false, and it can't be true. So it can be the third color.
I see. Yeah, okay. Yeah, I get it. Yeah. All right, thanks.
All right, any other questions?
Yes, Professor, just a bit of a tangent question.
Yeah.
You mentioned earlier that for 2 coloring, it can be solved in polynomial time?
Yeah.
So can we use the same mapping that we used here for all other NP problems to show that if there's only 2 literals, they can be solved in polynomial time?
No, I wouldn't go that far.
No, eh?
That would be it. No. The reason you can solve 2 coloring is basically, you know what a bipartite graph is? You have a bunch of nodes, 2 sets of nodes, and all edges go between the one set and the other set. There's no nodes within the sides. That's called a bipartite graph. And a graph has a 2 coloring if and only if it's a bipartite graph. And I bet you in 20 minutes you could come up with an algorithm for determining whether a graph was a bipartite graph.
Okay. But we wouldn't be able to use that reduction for other problems.
No.
Okay. Gotcha. Thank you.
Any other questions? People, how did you kind of follow this? It was kind of fun, eh?
Yeah, it was okay.
Yeah. Well, now I'm thinking about that.